Hello and welcome to the Space Above Us, Episode 26, Boosters and Engines. Last time, we took a look at the NASA facilities that would enable an army of men and women to design, build, and fly the vehicles required to get to the moon. We talked about the Goddard Space Flight Center for Operations and Computer Engineering, the Marshall Space Flight Center for designing and building rockets, and what would become known as the Johnson Space Center and the Kennedy Space Center for controlling and launching the missions. We also took a peek at some of the centers that were formerly part of NACA, which helped provide critical fundamental research. Today, we're going to be talking about launch vehicles and the engines that powered them. The success of Apollo can be directly attributed to the success of the Saturn family of launch vehicles. These mighty boosters were the first of a new era of spaceflight. Adapting old ballistic missiles got the job done for Mercury and Gemini, but it wasn't enough for Apollo. It would need a new generation of vehicles designed from the ground up for human spaceflight. So you ready? Let's light this candle. Before we really get started, I think it makes sense to do a quick refresher on how rockets actually work. Rockets are so notoriously difficult to build and fly that they become a cliché. The term rocket scientist is practically a shorthand for genius. But most of the difficulty comes down to the real nitty-gritty details. In the abstract, rockets are almost laughably simple. The goal of any rocket is to take some material, accelerate it, and throw it out the back, thus propelling the rocket forward. They accomplish this by burning fuel, which generates a bunch of super-fast gas that is then expelled through a nozzle, which makes the gas even super faster. But since rockets fly where there is no air, if they want to burn things, they need to bring their own source of oxygen. Ignoring solid-fueled rockets for the moment, a really simple rocket could be built with a tank of fuel, a tank of oxidizer, a place to mix and burn the two, and a nozzle to speed up the exhaust. This works fine until you get to a certain scale and discover that gravity alone isn't enough to pull sufficient fuel and oxidizer into the combustion chamber. A slightly less simple rocket can use some sort of pressurizing gas to push the propellants out of their respective tanks faster than gravity. But that makes the propellant tanks really big and heavy, and still won't deliver the propellant fast enough for a really big rocket. So the next step up the complexity chain is to add some pumps that can force propellant into the combustion chamber in the volumes required. So let's see what we have now. A combustion chamber where fuel and oxidizer can mix and burn, a fuel tank, an oxidizer tank, a couple of pumps to bring fuel and oxidizer into the combustion chamber faster, a bunch of pipes to connect it all together, and of course, a nozzle in the back to expel the resultant gas. On paper, there's really not that much to it. We'll get into some of the details of engines in a few minutes here, but to give you a sneak peek of where the complexity comes from, consider these questions. How do you keep the combustion chamber and nozzle from melting? What's the best way to inject the fuel and oxidizer into the combustion chamber? How do you spin the pumps fast enough to deliver propellant quickly? How do you do all of this while keeping the entire structure as light, reliable, and cheap as possible? These were the questions on the minds of the Army Ballistic Missile Agency, or ABMA, in the late 50s. As you recall from the previous episode, the ABMA is where Wernher von Braun and his German buddies were put to work on rocket technology. After their success with the Redstone and Juno rockets, they were approached by ARPA, the Advanced Research Projects Agency, to start on a super heavy rocket. This new rocket was to use as much existing technology as possible, but still push the boundaries in terms of scale. To deal with tight budgetary constraints, the proposed booster was built mostly with parts from other rockets. It had a cluster of 8 fuel tanks, which just happened to be the diameter of the tanks used for Redstone, which surrounded one large oxidizer tank, which just happened to be the same diameter as the tanks used for the Jupiter rocket. The resulting beast of a booster became known as the Saturn. Get it? It's the sequel to Jupiter. Unfortunately for ABMA, there inevitably came a point where someone, somewhere in the Army chain of command asked, what the heck do we need this giant rocket for? If your goal was to launch bombs, you didn't need a rocket that big. If your goal was to launch a bunch of people, well, why does the Army want to do that? There was simply no good reason the military needed such a big rocket. Fortunately for ABMA, there was a hot new government agency by the name of NASA that could use a big rocket. ABMA became the Marshall Space Flight Center, and Saturn became a NASA project. One thing I think is important to point out here is that Saturn, and the engines that powered it, were being worked on well before the decision to go to the moon. In fact, it was their presence that allowed such a bold goal to be set in the first place. One of the cool ideas about Saturn was that it wasn't just one rocket, but a family of rocket parts. The idea was to design a bunch of rocket stages that could be more or less interchangeable based on what the mission called for. For example, the Saturn I would use the original first stage developed for ARPA, known as the S1, along with an S4 upper stage. The never-flown Saturn C2 would use an S1 first stage, S2 second stage, S4 third stage, and an S5 fourth stage. By focusing on stages that would work together, they could keep their options open before committing to any particular rocket configuration. When the mission became more clear, they could then pick the appropriate configuration and actually begin bending metal and building the rocket. The stage that would go on to fly most often was the S4B, an upgraded version of the S4. It was about 60 feet tall, 20 feet wide, and served as the second and final stage of the Saturn 1B rocket and the third and final stage of the Saturn V rocket. What makes the S4B special is what it used for fuel. Most rockets, even to this day, burn RP-1 as fuel. That's rocket propellant 1. RP-1 is basically just really refined kerosene, the same stuff people used to burn in lamps. That wasn't nearly fancy enough for the S4B, though. No, the S4B burned liquid hydrogen. Hydrogen is fantastic as rocket fuel. Using liquid hydrogen and liquid oxygen together is just about the most efficient rocket possible. But rocket engineers had hesitated to use it up until this point because it's incredibly difficult to work with. First, it's super crazy cold. Now, I know what you're thinking. Hey, liquid oxygen is pretty cold too. No, you don't understand. Liquid oxygen is already about 300 degrees below 0 Fahrenheit, but you have to go another 120 degrees to find liquid hydrogen. That's about negative 185 and negative 250 in Celsius, by the way. Not much warmer than absolute zero. Because of this, it's constantly trying to boil off or do weird things to materials that aren't used to those kinds of temperatures. But that's actually probably the easiest thing to deal with. It also makes metal more brittle, resulting in tons of microscopic cracks. And since hydrogen molecules are so small, just 2 hydrogen atoms being buddies, they'll slip right through those cracks. But that's not all. Not too long before this whole adventure got started, liquid hydrogen was still something being made in small quantities in the lab. The S4B needed 250,000 liters of the stuff, and it was the smallest stage of the whole program. And if all of that wasn't bad enough, there's the inconvenient fact that hydrogen burns with a nearly invisible flame. This meant that working with it and testing it could be really dangerous. While testing stages that used liquid hydrogen, one manufacturer kept having issues with invisible fires sprouting up. Their solution? You can't make this up. Have some dudes in heat-resistant suits walk around holding brooms in front of them. If the broom caught fire, they found a leak. God, I love the space program. All of this trouble was worth it because liquid hydrogen was just so efficient. 40% more efficient than RP-1. So get your brooms out and hold them at arm's length, because we're going to the moon. At the bottom of the S4B was the engine responsible for turning all of this liquid hydrogen and liquid oxygen into thrust, the J2 engine. The Rocketdyne J2 engine was one of the first ever large rocket engines designed to burn liquid hydrogen and liquid oxygen. It could gimbal, point, from side to side, was about 11 feet tall, 7 feet wide, and it put out about 230,000 pounds of thrust. One thing I've struggled with when talking about rocket engines is trying to bring the bonkers numbers back to a human scale. It's not easy, but let's try it. If you took a single J2 engine and magically had it running without any of the rest of the rocket, including fuel tanks, with 230,000 pounds of thrust, you could lift 2 or 3 average houses, or 100 cars, or 15,000 pugs. But the J-2 wasn't just a beast, it was an advanced beast. While most of the rocket would only be used for a few minutes, the J-2 at the base of the S-4B needed to turn on and fire again a few hours after launch in order to send Apollo to the moon. I'm not going to get into all the technical details of why this was so impressive, but I want you to imagine how hard it is to start a rocket engine on the ground. Now imagine doing it in space. Plus, you have to make sure that your fuel doesn't boil off, your components don't freeze, electronics don't fail. Trickiness abounds. As I mentioned, a single J-2 was used at the base of the S-4B. The J-2 was also used on the S-2 stage, which for the sake of time, I am going to basically skip entirely. Sorry, North American aviation fans. At least you'll get an episode on the command module. The S-2 was big, it used 5 J-2 engines, and it was used as the second stage of the Saturn V. Eagle-eared listeners may have noticed that we actually have enough parts now for a new rocket, the Saturn 1B. This vehicle was about 140 feet tall, 20 feet wide, and was used for the Earth orbital portions of the Apollo program. Need to test a command module? No problem. Lunar module? You got it. As long as you're fine with staying close to Earth, that is. For the first stage, it used the S-1B, an upgraded version of the original stage commissioned by ARPA all those years ago. And it used an S-4B as the upper stage. That's why it was the most used stage. Both the Saturn 1B and the Saturn V used it. The Saturn 1B doesn't really get a lot of credit, but it was an important part of the Apollo program. As I mentioned, it played a crucial role in testing the Apollo hardware in space, if close to home, but it also launched Apollo 7 and the crews of all 3 Skylab missions, and the Apollo-Soyuz test project. It may not get as much attention as its big sister, but if it was around today, it would be the second biggest rocket on Earth. Before we can talk about the Saturn 1B's big sister, we have one more bit of rocket technology to discuss: the F-1 engine. The F-1 is the unearthly monster of an engine that made the entire Apollo program possible. At a whopping 1.5 million pounds of thrust, just one of these engines was more than 3.5 times more powerful than the Titan II that launched Project Gemini. As of 2017, it has yet to be surpassed in pure brute power. But rather than go on and on about how crazy the F-1 engine is, how about some facts? The F-1 had actually been in the works for quite a while by the time Kennedy committed NASA to the moon. It was originally designed in the mid-1950s for use by the Air Force. In hindsight, it was complete overkill for anything the Air Force had in mind, but there were a lot of crazy and interesting ideas floating around in the 50s. There wasn't really a firm mission or requirement for the F-1 when they started work, but it was obvious that space was going to be an important part of the nation's future. Since it takes so long to develop a reliable rocket engine, it made sense to just roll the dice on something big and get to work. Contrary to what you might think, the F-1 was explicitly made to not push the limits of technology. Envisioned as a big, dumb booster, everything was to be kept simple and use existing tech whenever possible. It burned RP-1, and it had the same general layout as previous engines. Simply take engine tech we already understand and make it bigger. Of course, that never really works out when working at the limits of technology. Problems inevitably arose when attempting to do things the old ways, and new techniques had to be invented in fabrication, metallurgy, testing, dynamics, and all the fun stuff. Since the long tortured history of the F-1 would be too much to get into in a single episode, here's just one example of how difficult it was. One major issue with rocket engines is combustion instability. This is when the flow of the superheated gas from the engine becomes turbulent and unpredictable. You don't want this since it makes it nearly impossible to predict thrust levels, structural loads, thermal loads, and other dynamic aspects of engine operation. In short, it can make your engine go boom. When engineers tried to figure out what was causing instability in the F-1, they hit a significant roadblock. Nobody really knew how combustion instability worked. There was no theoretical framework for it, and computers at this time simply weren't beefy enough to just simulate it. The solution to engines blowing up turned out to be blowing them up. Sort of. Rather than wait for combustion instability to happen on its own, small bombs were placed in the thrust chamber of the F1 and detonated to induce instability. This way they could at least definitively test how their latest designs would respond to combustion instability. From there, they still weren't quite sure what was causing it, so they would simply try different arrangements of baffles and injector plate designs to see how they held up in testing. Eventually, they came up with a design that would return to stable conditions quickly enough for it to not be a major impact. As a fan of Formula One, the European speedy race cars, I couldn't help but compare the F1 engine to, well, an F1 engine? These days, a Formula One engine clocks in at around 1,000 horsepower. It's a veritable engineering miracle for an engine so small and efficient, and I don't want to hear your complaints about the sound as compared to the V8. It sounds great. Horsepower is sort of a weird concept to apply to a rocket, but based on my poking around, the Rocketdyne F1 engine clocked in at around 22 million horsepower. That means that if we play a little fast and loose with the numbers and assume that Formula One has 20 cars per race, 20 races per year, and about 60 years of races, and add up all of that power, we'll get 24 million horsepower, which means that just one F1 engine is about as powerful as the entire history of F1. All of that hard work on the F1 enabled the monster rocket that we've all come to know and love, the Saturn V. The Saturn V is probably the most iconic rocket in history. I think it's the rocket most people envision when they think of the word rocket. At 363 feet tall, it remains the largest rocket ever flown, and is likely to retain that title for years to come, despite new super heavy boosters on the horizon. Its first stage was the S1C, powered by 5 of those ridiculous F1 engines. 5 of them. The second stage was the S2, carrying 5 J2 engines. And topping it off was the S4B stage with its lone J2 engine. In an attempt to make the numbers make any sense at all, here are a few calculations I did about the Saturn V. It could play tug of war with 30 Boeing 747s and win. It could launch 100 Mercury capsules into orbit at the same time. It could launch 8 times more than a modern Atlas V rocket. It could send 12,000 cats to the moon. BYO spacesuit. The numbers are just crazy. I think we just need to accept that the Saturn V is beyond any scale that humans can comprehend. It was first launched in an unmanned test flight in November of 1967. Just over a year later, on its third ever flight, it propelled Frank Borman, Jim Lovell, and Bill Anders to the moon on the flight of Apollo 8. In all, it flew 13 times and didn't fail once. Okay, SA-502 had a couple of issues with the J2 engine, but the mission was still a success, so let's not quibble. Since it was the main launch vehicle for the Apollo program, we are going to become very familiar with the Saturn V over the months to come. There are 2 other rockets that I promised to talk about today, and they are the Little Joe and the Nova. Let's start with the Nova. If the Nova had ever been built, it would have made the Saturn V look reasonable. Its first stage would have used 8 F1 engines. It probably would have used nuclear engines for the upper stages. We'll never know for sure because its raison d'etre was direct ascent. As you'll recall, direct ascent was the concept of flying directly from the surface of the Earth to the surface of the Moon, with no orbits, rendezvous, or anything else in between. To accomplish that, a rocket of unthinkable proportions would have been required, and that was the Nova. As time went on, however, it became apparent that even the Nova wouldn't be enough to make direct ascent work. Once it became clear that an alternative was required, lunar orbit rendezvous won the day, and it worked just fine on a Saturn V. No Nova for us. It's a good thing that the Nova was abandoned since it almost surely would have resulted in NASA missing the moon landing deadline, but part of me will always wish that this ridiculous vehicle had had a chance to fly. What did have a chance to fly was the Little Joe rocket. The Little Joe didn't play a big role in Apollo. You might even say it was little. But that doesn't mean it wasn't important. Back in the early days of Apollo, before most of the hardware was ready, they needed to test some of the components in flight-like conditions. Of particular interest were the parachute system, the abort system, and the aerodynamic characteristics of the command module. Rather than try to simulate the whole thing on a computer, engineers put together the Little Joe rocket. Despite being pretty minuscule compared to the behemoths we talked about earlier, the Little Joe was nothing to shake a stick at, or a flaming broom. It was over 50 feet tall and could carry 3,000 pounds. My favorite part of the Little Joe test program was a particular test of the automated abort system. Since rocket disasters tend to happen pretty quickly when they do happen, NASA wanted an automated system to detect if the rocket was failing and initiate an escape to safety for the astronauts. During a test of this system, some wires got crossed and the vehicle started to roll. Not too quickly at first, but it just kept rolling and rolling, faster and faster, and then it started to fall apart. Not realizing that this wasn't part of the test, the automated abort system did its job. Noticed the rocket was rapidly becoming not a rocket, and initiated an abort. The escape tower fired, pulling the boilerplate Apollo capsule away, leaving it to gently touch down a few minutes later under its parachutes. The rocket had completely failed, but the engineers couldn't have asked for a better test. And thus concludes our little tour of the boosters and engines of the Apollo program. We'll be getting into more detail about all of this as we cover the missions themselves, but I wanted to make sure that you all had a good understanding of the launch vehicles used throughout the program. For those of you who really know what's up and are shouting at your phone, "Hey, what about the instrumentation unit?" Fear not. We'll be talking about the brains of the rocket, alongside the brains of the capsule and all the software that made it run, next time. Burning fuel and lofting payloads is obviously an important part of any space program, but without software to guide the payload on its way, it would all be for naught. Join us next time as we explore the computers and software that made the moon landing a possibility. Ad Astra. Catch you on the next pass.